Okay, guys, I'm taking a kid to a doctor's appointment this afternoon, but we're going to go through lesson 7.5, or excuse me, 7.5.5.7. This is the last section of the chapter. Thank goodness for some of you. Like, you're probably like, get this out of here because we're ready to be done with proofs, right? Or maybe that's all of you. I have no idea. But this one is kind of a different beast, triangles and coordinate proof, and I don't give you too hard of proofs on the homework assignment, but these are just like different things that we're allowed to prove, okay? So the first, like, probably half or 3/4 of your homework assignment are going to have to do with just like setting up a coordinate proof, okay? Like, not even proving anything, like how would you do this, okay? So we're just going to talk about like good common practices for doing a coordinate proof, okay? So what you're doing is you're using a coordinate plane to like position a triangle somehow, some way, okay? So here's the deal. If we're going to be talking about, let's say, an isosceles triangle where two of the sides are the same, you're going to position this triangle on your coordinate plane, probably so that either this, like 0, 0 is one of the coordinates on the bottom, so that he looks kind of like this, or I'll show you another option here in just a second, okay, for an isosceles triangle. But here's the deal. So over here, like, the way that they have this position is like this corner is 0, 0. Okay, they went ahead and said this coordinate is a coordinate of 2a comma 0. Okay, now maybe you want to say that this is like 10 comma 0, right? If that's 10 comma 0 and this is an isosceles triangle, then this dot right here will be at 5 comma something, right? Okay, but here's the problem. We don't want to use exact numbers because we don't, if we prove it with exact numbers, then somebody might say, oh, but wait, it only works with 10 and 5. It might not work with 6 and 3. So what we do is we use what's called arbitrary values, like variables, okay? So we use like 2a and b in order to prove it, so that no matter what A is and no matter what B is, we can show that it works, right? So what they do is they set this up nicely with coordinate points, and they say, okay, this is 0, 0. And let's just pretend that this guy is something called 2a comma 0, okay? Well, then this coordinate right here would be going over half as far, which would be like if this was 2a, right? The distance from there to there is 2a, then this would just be 1a. That's where they get this coordinate right here. And how tall is he? How high up does it go? It goes to b, right? Okay. We don't know how tall it is in comparison to a, so we're just going to list it as b, okay? Now, another thing that you could do if you have an isosceles triangle is, let's say you do this, where you have it looking like this, right? This is your isosceles triangle. In which case you don't use 0, 0 here, but what you can do is you can say, okay, this dot right here, let's call that a comma 0, right? Like 0 is going to be the y-coordinate because it's on the x-axis, okay? And that means a comma 0 means the distance from here to here is a. We've gone over a, right? Okay, but then what would the coordinate of this be? Well, that would be negative a comma 0, right? We could do that, okay? And then what would the coordinate of this dot be? Like that third point, right? Well, we know he's going to be 0 comma something, right? Because he's on the y-axis, 0 comma something. And I don't necessarily know that this distance is the same as these two, right? I don't know that that's a units tall. So let's just call it b, right? And that would be an isosceles triangle as well, just positioned a little bit different than that one is, right? Okay. And then we would use those values of a and b to prove things, right? Like, can I prove that these two angles are the same? Like if I look at the slopes and stuff, right? Like I could do things with that. But again, I don't want to use numbers for your A values and B values, because then somebody could say, well, but that would only work if the numbers were 10 and 5, or, it wouldn't work if it was 8 and 4 or whatever. So, that type of thing. Okay. Example 1. Again, this is just like a get it in position so that it works, right? Okay, so position and label, I want a right triangle. Okay, anytime you see the words right triangle, we're going to position this, so we're going to use 0, 0, and we're going to use this 90-degree angle right here. Anytime you see a right triangle. I don't want to move my right triangle over here, like that would be stupid. Like, use the already existing 90-degree angle that is there on the coordinate plane. So we're going to use that angle, all right? And it's triangle ABC, and the legs of the triangle are AC and AB, okay? So the legs are going to be these guys. And if the legs are AC and AB, then that tells you which one my vertex is. Whoa, what just happened? Okay, AC and AB, that tells you my vertex, which is this guy right here, like your 90-degree angle, right, is positioned at 0, 0, but he is named A, because that's the only way that AB and AC will both include A, is if that guy is the 90-degree angle. Okay, so let's put, it doesn't matter, let's put B here and let's put C here. Those two you can change, it doesn't matter, okay? They want AC to be 2A units long. That means the distance from here to here is 2A, okay? So if that's the case, then what would the coordinates of this guy be? The coordinates tell you this is how far you go to the left and to the right. This is how far you go up and down, right? Like that's what the X and Y coordinates are. So if this has a distance of 2A, then your X coordinate's going to be 2A, comma, 0, right? Because we're not going up and down any, okay? And AB, they want to be 2B units long. So the distance from here to here is 2B. Now, if that's the case, then what would the coordinate of that be? He would be 0, comma, 2B, right? It's 2B units tall. And then just to finish out my triangle, like the hypotenuse would look like that. But I have my 3 vertices, are those 3 right there. And then I would eventually, they don't ask us to do it here because they're just starting us out. They're just getting our baby steps figured out. I could then eventually do some proofs with that, okay? All right, so there you go. Example 2. Name the missing coordinates of the isosceles triangle. Okay, isosceles means 2 equal sides again, right? So, and they have it labeled right here for me. They have that these 2 little tick marks are the same, okay? All right, they have some of these already labeled. They say that this is 0B, meaning that it's 0 left and right, but it's B units tall. So like the distance from here to here is B, right? Like that's what the Y coordinate tells us. Okay, then they say over here, this dot, this vertex, is negative 2A. Okay, what that means is I've gone 2A this way, and then I need to figure out what the Y coordinate is. Well, I haven't gone up or down at all, so that Y coordinate's going to be 0, right? But it's 2A units from there to there, right? And I'm going negative 2A because I'm going to go to the left, okay? If this is an isosceles triangle, from here to here, wouldn't that be 2A as well? Right, like that distance. So I'm going to say that this coordinate is 2A, comma, again, we're looking at this vertex, 2A, comma, 0, because we're not going up and down at all, right? Okay, so those are my, again, we want to use variables. Those are my arbitrary values so that, you know, like I could do proofs with that and it would hold, right? A proof has to use arbitrary values so that you know that it works for every value, okay? Good? All right. That was example 2. Let's go to and look at some example 3. Okay, this is where they actually have us do a proof. Okay, so let's take a look at this, and I'm going to kind of fuddle through their proof a little bit. I'm not going to, maybe we won't even do this proof. Maybe we'll just talk through it, okay? So what they've done here is they are trying to show that these 2 triangles are congruent. Congruent means same shape, same size. And if we have coordinates like this, one of the things that we can do is we can do like side, side, side. If I'm able to say that this side is the same length as this one, that this side is the same length as this one, right? And this side is the same length as this side, then by side, 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 this triangle would be congruent to this one, right? Well, how do I do side, side, side? Well, I have the coordinates, and if I'm trying to find the length of this side, I would do the distance formula from this guy to this guy, right? Okay, and then I would do the same thing here, and I would do the distance formula from this guy to this guy, okay? So let's pick on, is that the first one that they have us do? Yeah, yeah. They want us to do DC first. Yep, that's this one. Okay, so I'm just going to do this first one, and then we'll do GH, and I'll show you how like those 2 match up, right? Okay, so first things first. Blah, blah, blah. Let's go over here. Okay, so when I'm doing my distance formula, I'm looking for how far apart are negative A and negative A, right? I don't like their things. I'm just going to scribble this out, right? I'm just going to do my square root, okay, because we don't have to write all the steps out, because we do some of them in our head. So how far apart is negative A and negative A? Like they're the same far apart, right? So they are 0 units apart. How far apart is B and 0? Like if I would do B minus 0, that would be B units apart, right? Okay, so 0 squared is 0. B squared is B squared. And 0 plus B squared is B squared. And if I take the square root of B squared, it is B. Okay? You probably knew that just by counting, right? This is a vertical line. What is the distance from here to here? That's B units, or whatever this coordinate is, right? Like, that should hopefully maybe make sense to you, right? If we do the distance formula for this guy, it ends up being B as well, right? Like A and A, those aren't any far apart, but the distance from 0 to B, like maybe this was the number 5, I don't know. The distance from 0 to 5 would be 5, right? Like this side would be 5. But they're using B instead as an arbitrary value, so that's a distance of B, right? And then they would go through and do the distance formula. And the distance formula gets really disgusting when they do this B over 2 guy, right? But we could do it like we would have decimals and all the things, but we would make sure that this guy matches up. And then after we do all 6 of our distance formulas, which are kind of disgusting, we could say by side, side, side that those two triangles are congruent, right? If the coordinates are like in that way, okay? So now that I've proven it for that arbitrary value, right, I can go back to this triangle, and as long as it has this setup, right, of those coordinates, then I could say that those triangles are congruent. For example, let's say A is going to be 7, right? So if this coordinate right here is at -7, comma, let's say B is 12. Okay, so if that guy's at -7, 12, this guy would be at -7, 0, right? Okay, this guy would be at +7, 0, and this guy would be at +7, 12, right? Okay, this dot right here would be at 0, comma, 12 divided by 2, or 6, right? So we know that if it's in that setup, then by side, 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 those triangles are congruent. But I don't have to redo the whole proof every time I switch those numbers, because as long as the A's and B's are in that relationship, then those triangles will no matter what be true, right? It's kind of like downsizing, right? Like, or upsizing. Like, let's say I'm building, something that's going to have like this path, and maybe it's on a triangle. It's probably not going to be a triangle. Maybe it's like a rectangle, like a house or a barn or something, right? And I do that, and I then decide to downsize. I don't have to reinvent the wheel to figure out if my one spot is going to be congruent to my other spot. I just keep them in the same proportion, and it would be okay, right? Whatever. Anyway, let's move on. Let's go to, here's another proof, but I don't want to. Yeah, let's talk about this one. Example 4. So what they have going on here is they say, write a coordinate proof to show that the two lines are equidistant from a third line. Okay, so what we're given is that AB, which is this guy, and EF are the same distance away from CD. Okay, so this distance is the same and this distance is the same. So what they've done here is they've said, let's look at just A and E, right? They've had A at 0, 0, and E is at 2A, 0, meaning the distance from here to here is 2A. Okay, and if this distance is the same as that one, then that would make this just 1A, comma 0, right? Like, that's the same distance, okay? Now, they've done the same thing up here, and they've said, okay, let's put this guy at AB. Let's put this guy at 3AB. Then this guy would be at 2A, comma B, right? Like, this is the same distance away from there, right? 2A is the same distance away from A and 3A, okay? So they put those arbitrary values in there, and that's kind of hard to understand, but it's fine. Whatever. We'll just go with it, okay? They want us to show that all of those lines are parallel, or I guess essentially AB is parallel to EF, okay? And what makes two lines parallel is you look at their slope, right? So if I'm looking at the slope from here to here, I do y2 minus y1. y2 is B, minus y1 is 0. x2 is A, minus x1 is 0. Okay, B minus 0 is B, A minus 0 is A, so this guy has a slope of B over A, which is kind of interesting to think about, okay? Now, we have the same thing going on here, right? I want to find the slope from E to F, and I want to see if it ends up being B over A, meaning that those two would be parallel. So I'm going to do y2, which is B, minus y1, which is 0, over x2, which is 3A, minus x1, which is 2A, right? B minus 0 is B, 3A minus 2A is A. Oh, that also has a slope of B over A. So I know for sure that those two lines are parallel to each other. Okay, I understand that this is super hard to understand when you have B's and A's and all the things involved, but the reason why we have to do that is so that we know that it works for every value. Like I can plug whatever I want to in for A and B, and as long as I keep the A consistent all the way through, then over here, then those lines will be parallel. Whatever. That's how this works, okay? Thankfully, I don't give you anything like too intricate like that, okay? What I'm probably going to give you on the homework assignment is something that looks like this. The Polynesian Triangle is a triangle formed between the 3 Pacific island groups that forms the South Pacific region known as Polynesia. Whatever. The approximate coordinates for latitude, longitude are these things. Blah, 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 blah. Oh, they want us to classify this triangle. All right, let's talk about classifications. In order to classify, you could have a triangle that all 3 sides are the same, in which it is equilateral. That's supposed to be an E. Equilateral, okay? Which means all 3 sides. 3 sides equal, okay? It is also equal angular, which is another thing, but we'll talk about that more in chapter 7, I think. Equilateral, equal angular, 3 sides are equal. If it is 2 sides equal, it's called isosceles. 2 sides equal. And if no sides are equal, then it is scalene. Okay, that's just general kind of vocabulary. And we've talked about those already before, like the last section was about equilateral isosceles triangles. So we want to see which type of triangle this is. We want to classify him. And so what we're going to do is we're going to look at the distance of each side. We're going to do the distance formula, okay? So I'm going to do the distance formula of that guy. Okay, and I'm going to do, I should make these bigger because we have decimals. There we go. Okay, and we're going to do the last one, distance formula, and this will be our last example, and then I'll tell you what homework is, and then we'll be done. Okay, so there is that. All right, I want to know how far apart 21.3 and 40.9, negative 40.9 is, okay? And that is going to be 62.2, I believe. Right, 62.2. Yeah. Then I want to know how far apart negative 157.9 and positive 174.9 is, okay? I'm going to use a calculator for that one. Okay, since one is positive and one is negative, we are going to add those distances together, right? And I get like 332.8, okay? All right, if I'm trying to find that distance, I'm going to square that. And I'm going to add to that 62.2 squared. And then I'm going to take the square root of that. And I get that distance is, I'll write it in a different color, 338. Let's say 6. 338.6. Okay? All right, and I'm going to do the other side. So I'm looking at the distance between 21.3 and negative 27.1. And that is 48.4, I believe. Okay? Now I'm looking at the distance between this guy and negative 109.4. And that is going to be, I'm going to do some math in my head, 0.5, 57 minus 9 is 48.5. 48.5, yeah. Okay, so 48.4 squared and 48.5 squared. And we're going to do that. Oh, come on. All right. How on a phone okay, whatever. I got it to work. 48.4 squared plus 48.5 squared. And then I take the square root of that answer. And I get 68.5. All right. So the fact that looks way shorter. Or like they look equal. But this is way shorter than this one. Interesting. Yeah, that's right, though. Whatever. Okay. I know now for certain that this is not an equilateral triangle, right? Okay. Let's figure out my third side. So I've got 40.9 and negative 40.9 and negative 27.1. So how far apart are those two negative numbers? 40.9 minus 27.1. And I got 13.8. And then I want to know the distance between 174.9 and 109.4. And that is 0.3. Carry the 1. 4. Carry the 1. 8. 284.3. I'm just going to check it because I don't trust my math right now. 109.4 plus. because this one's negative, right? And this one's positive, plus 174.9. Ah! It didn't do my point as a... Oh, I can go back. How fancy. Oh, yeah, 284.3. Man, these phone calculators have really, like, upped their game. Okay, 13.8 squared. I'm going to square both of those, and then I'm going to take the square root. And I get, whoa, 284.6 is that many mileages. I think they were in miles. Are we in miles? No, we're not in miles. We're in latitude points, latitude and longitude points, which is not in miles. It's not even in kilometers or anything. It's like points of latitude. Anyway, okay. The fact that those three are all different means that this is a scaling triangle. There you go. So that is all I think that we needed. Yeah. Because the length of each side is different, the triangle is scalene. Okay. All right, there you go. Homework assignment. Here you go. Is, oh, I didn't write this down. Page 339, 1 and 2 and 5 through 8, all, and which ones? 14 and 15. 14 and 15 are going to be like the ones that we just did where you're doing coordinates and you're trying to figure out and classify the triangle. There you go. So 14, 15. The first ones on this first page are going to be like set up the coordinates and find the missing coordinates type of thing. Okay, so there you go. I think it's 14 and 15. I just lost my train of thought already. Yep, 14, 15. Okay, I know this stuff is kind of like foreign to you and all of the things, but, you know, yeah, we'll get through it. It'll be fine. Okay, all right. Work on your homework assignment. Goodbye.